Greetings everyone, welcome back to Calc 2, still on our steady climb to getting prepared for multivariable calculus. Now we're moving into the unit where we're going to talk about vector functions. And basically, this is sort of like another upgrade to the way that we look, or one possible way to analyze functions. Okay, so we started with plain ordinary algebraic definition of functions. And then in the last couple of units, we moved up into looking at parametric equations. And then on the side, we also did polar coordinates, which went along with parametric equations a little bit. Parametric equations was an upgrade to the way we think of functions and allowed us to include many more shapes, curves that weren't previously considered functions. And now another slight upgrade to parametric is vector functions. And really what it is, it's practically the same thing, except we use the concept of vectors to bring the two directions back together into one function object. So a vector function is basically where you're still separating out the different dimensions like x and y, but you're putting each of the t functions, right? X is going to be some function of t, y is going to be some function of t, but you're putting them in a vector type of listing. Okay? In parametric form, the only difference is the x and the y basically just give a point. Whereas in the vector format, you still get those same coordinates every time you plug in a value of t, but the difference now is that it is treated like a vector. And remember, vectors bring just a little bit more to the table than just the ordinary points or numbers. Okay? They have other operations that we can do to them and have a larger encompassing meaning behind using them. So, for example, when you're in parametric form, right, you'll be looking at a curve that is formed from your parametric equations. In this case, I have the ellipse that's being formed from x equals 3 cosine t and y equals 4 sine t. The flow of that ellipse is in the counterclockwise direction, as we're accustomed to seeing when we typically do these kind of circular parametric forms. And if I pick any particular t value, then I will calculate a point on that curve. Whereas with vector functions, I can take the same coordinates. X is 3 cosine t, y is 4 sine t. And instead of just getting the location when I plug in a t value, notice I'm actually getting a vector here, right? The vector is pointing to the spot on the curve. And as the t changes, so does the vector. The vector actually moves along with the curve. So your curve will be moving in some direction, and the vector will be pointing from the origin to the point that you're on that curve at any given t value. So that vector can actually have some meaning behind it. Maybe you're doing a torque, or maybe you're doing some sort of momentum or something like that. This r vector right here can have some deeper meaning rather than just a location. Okay, you can use it to pinpoint an origin of something and have that as some sort of position vector from that point of origin. The calculus that's involved with vector functions is not that much different either, except that when we were doing parametric functions, remember, we still had the goal of looking for dy dx as our quote-unquote main derivative. And that's because we were only doing tangent lines on the curve still, like we were doing before. When you start talking about vector functions instead of parametric equations, you get a slight upgrade on your derivatives there, where I'm still going to be taking the derivative of each individual component, but notice now if I don't want to divide them to get the dy over dx, which that's what you would do over with parametric, right? I would do dy dt over dx dt to get my original derivative slope of the tangent line. Here, in vector functions, if I can take the derivative of it, right? I take the derivative of the entire vector function, which just means I take the derivative of the components. And that's the same thing as over here as doing dy dt and dx dt, right? That's all this is, dx dt and dy dt, right? F prime, g prime are the two functions there. Except if I leave it in a vector form. See, like right here in our example, the derivative of each piece separately still gives me a vector. However, we can actually call this the tangent vector. If I were to graph this vector at the point, which I have right here, notice what you get is a vector from the point that we're in discussion, pointing in the direction that the motion is going. And that's because that's the tangent vector. It's a representation of a small bit of change as the motion on the curve is progressing. So it actually has some deeper meaning rather than just a tangent line. We can actually get a tangent vector out of this. And that's where the concept of velocity can eventually come from, and other types of rates of change measurements such as that. Okay, so vector functions is a slight upgrade from parametric equations. A lot of the math is going to feel exactly the same as parametric equations. The calculus is going to be more inside now, though, rather than doing the derivatives and then bringing them together to form dy dx. When you're doing the calculus on a vector function, you'll simply be doing it to components. Same thing with the antiderivative. If I want to do an integral of a vector function, I'm really just doing the antiderivative of the individual components. If it's an indefinite integral, of course, you will have a constant vector, right? That's your plus c, but it needs to be a vector because both the x component and the y component are going to have different c values that can come in from your integration, okay? Or you can do a definite integral instead of an indefinite, right? Indefinite is where you get the plus c. You can do a definite integral with limits, in which case each of these would have the same limits from a to b, whatever, okay? Most of the time, the antiderivative, when it's applied to one of these vector functions like this, is mostly for doing the antiderivative of something. Like you started with a derivative and you want to build back up. And we'll be doing some of that with projectile motion as well. Okay, so vector functions is a slight upgrade from parametric equations. And just like parametric equations, you can actually have it with more than just an x and a y. It doesn't have to be just the 2D vector stuff that I'm drawing here right now. Don't forget, we've talked about vectors in three-dimensional space. And moving up into multivariable calculus, a lot of the calculus is going to be in three-dimensional space. All of this stuff works exactly the same in three-dimensional space, in four-dimensional space, in five-dimensional space. Even though we can't picture those, it still works through those in a more generic way. Okay, so vector functions, slight upgrade from parametric equations, in such that I can actually look at positions as vectors, and I can also get tangent vectors, and I can still talk about the curve itself, but then I can talk about maybe some of the things that are going on behind it as well, using the vectors. Let's get some examples of doing the everyday values, limits, domains, calculus of vectors, and then let's also get some examples after that of how these can still be treated as vectors with those special vector operations, dot product, cross product, such and so forth. Before we look at those other examples, just going to show you this graph that we were talking about on the board. Notice it is the two pieces, 3 cosine and 4 sine, right? That's my parametric function here. And GeoGebra is still treating this as a parametric function. However, I also have a vector right here called r that I'm forming using the coordinates from the parametric. So if I just leave it as is right now, as you can see, the point right here, the parametric equation just gives us the points as it's supposed to. And you can see the flow is in the direction that we discussed. Of course, the vector function gives us this r vector, which always points from the origin to the point on the curve. And then, of course, we would also be interested in the derivative, which would, in this case, would be the tangent vector. And notice there it is right there. This is the tangent vector. And you form this vector just by doing the derivative of each of the components. Notice the tangent vector is still tangent to the curve, much like we're accustomed to seeing tangent lines. But instead, we now have a vector that's acting sort of like a line and uses the direction to also describe not only the direction that the flow of the graph is going, but also a size as to how much it would want to move in that direction, and an actual derivative size to the vector. So now what you need to also see is that all of the operations and all of the analysis that we've been talking about in calculus for the past couple of courses still works the same with vector valued functions. We just get more opportunities for information when they're in vector form. Okay? We can still do domain and continuity. We can still do limits. All right? We still graph things very similar to the way we did before. And since they're vectors, we still can do dot product and cross product mixed in with the rest of the function stuff. Okay, so let's go through all of these examples here. List the domain and discuss continuity of the function r, vector function, 1 over t minus 3, comma, e to the 3t plus 1, comma, ln of 10 minus t. So yeah, look, that's a three-dimensional vector valued function, right? So it's in the 3 space that we've talked about before, the x, y, and z axes. And it's a function that is some curve that moves throughout the space. How do I know it's a curve and not some sort of surface, which when you start moving into the 3D world, right, you start having functions that can be surfaces. I know that this is a curve and not a surface because there's only one independent variable. And you're going to see that throughout all of the vector functions that we discuss here. We're not actually moving up to the full range of multivariable yet. We can increase the dimensions, which is what we're doing when we go into the 3D versions here, but there's still only one independent variable. So everything we're doing here is still curves. Okay, not upgrading to surfaces yet. Surfaces is reserved for multivariable calculus. Okay, so now what about the domain and the continuity here? Well, those sort of go hand in hand, right? If something is non-existent, if there's a point not in the domain, you tend to not have continuity there, right? So let's look for those sorts of things. Okay, so right here, I'm noticing right here that t can't be 3, right? And right here, for the ln, remember we can't do the ln of a negative number, so that means right here that t has to be less than 10, right? So t can't be 3 and t has to be less than 10. So then my domain is going to be from negative infinity all the way up to 3. Can't have 3. Union with 3 up to 10, right? And I also can't have 10 because 10 minus 10 is 0. And really what this is I'm just letting all of the pieces work together to create this domain. Okay? So then what about continuity? It's going to be continuous on all of the points that are in the domain, right? So in other words, I have a discontinuity right here. A discontinuity at t equals 3, right? And it'll be some point in space that you would figure out by plugging in values that lead up to it, because I can't actually let t equal 3. But I definitely have a break there. And then, of course, I have the end of the domain at t equals 10. So sort of like a discontinuity there, too. It's more like just an abrupt end. And it's an open circle, right? It's going to not go towards that right there. It's actually going to have some sort of negative infinite limit going on here, right? Because that's what logarithms do when you let them approach zero. Okay, so now what about limits? Again, same idea that you've been talking about for the longest time here. You need to consider, all of the different pieces. For example, the limit as t approaches 3 from the right. Of something linear, I can just plug that in, right? Right here, this can be 5 times 3 plus 7 for that piece of the limit there. Right here, though, you have to remember that the square root, I'm only going to be defining from the positive side, and this is 3 minus t. So if I'm approaching 3 from the right, that means it's coming down from 4, right? So actually, this is going to be non-existent or imaginary. Okay? Because I'm approaching from the right, and this is a minus right here. For example, pick any number to the right of 3 on a number line. 3 minus 4, 3 minus 3.5, 3 minus 3.1. You're still going to get a negative number here. Okay? So the value of my limit here is, for real numbers, not defined. Right? So not defined. Okay? Also, we've talked a lot about the limit as something goes to infinity. The limit as t goes to infinity here of this. And again, it works just like any other limit that you've done. I've just got 3 pieces to consider that limit of. So as t goes to infinity, 1 over t is going to go to 0, right? I have the limit as t goes to infinity of 1 over t is equal to 0. And that's going to go in both of these locations. Okay? So I've got limit as t goes to infinity of 1 over t is equal to 0. So that's basically sine of 0 and cosine of 0. And then I still also need to do the limit as t goes to infinity of this rational function. They're tied, right? T squared and t squared. So I'm going to end up with my coefficient fraction of 3 over 1. Okay, so what's the answer to this limit? I have the sine of 0, which is 0. I have cosine of 0, which is 1. And then the rational function here is tied, so I have 3 over 1, which is 3. Right? So I've got, this is the value of my limit. It's very similar to a curve approaching a point, right? But what's you have to imagine is it's like the vectors are slowly approaching something as t goes out to infinity. The vector is slowly getting to one particular vector, right, as t goes to infinity. And it may not be on an axis going to infinity. Remember, t is not actually drawn when we graph these things. Okay, so t going to infinity doesn't have to be infinity on an actual axis that we're graphing. This is just the vector that this function would approach if I let the input go to infinity. Okay, also very similar to parametric equations and even just the normal graphs. I can do a graph of the curve that these vector functions represent. I have a 2D one, I have a 3D one. Let's do those. Let's start with plugging in some values. Right, on one like this, I would probably want to just do some t values and then the f of t value, right? Okay. So for example, if I let t be 0, okay, f of 0, whoops, got to put my vector on there, f of 0 is going to be equal to 0 squared minus 4, which is going to be the vector negative 4 and 0. Right? Now what I'm going to do when I'm graphing these things is I'm going to let the vector always come from the origin. So really I'm going to be treating that like the point -4, 0. Okay? But you have to remember that we're actually carrying vectored information just in case I want to use it for any other mode of analysis while we're going down this line. Okay? So I'm also going to look at -1 and -2, and then let's look at 1 and 2 as such. Okay, so f of -2 is going to be the vector. I've got -2 squared is 4, minus 4 is 0. So I've got the vector 0, and then 4 plus 4 is 8. -1 squared is 1, minus 4 is -3. And then -1 squared is 1, plus 2 is 3. And then for 1, I'm going to have something very similar, except it'll be the -3 for this one again, but now it's going to be 1 minus 2, -1. Okay, already right there, notice these x values being the same would have made this traditionally not a function, right? This is going to be 2 points with the same x value. But since the input variable is t here for this vector function, it can still be a function. All right, so now I plug in 2, I get 0 and 0. Okay, so let's graph this thing. I'll put a little grid down here. And we'll just approximate a few numbers here. Oh yeah, we gotta go up to 8. 6, 7, 8. Yikes. -4 in the x. I'll just put a couple of marks here and here. All right. So what points did we come up with here? 0, 8. Remember, that's going to be a vector pointing up to here. This is the point right here, and technically I have to imagine it being a vector pointing up to that point. -3, 3. -3, 3 is here. And again, imagine I have the vector pointing here. Okay? Whenever we're discussing this, the point itself is not the f of t value. The f of t value is going to be the vector pointing to that location. Right? So technically we have vectored information there. I'm just using the points to help me graph the curve that it's tracing out. -4, 0, 2, 3, 4, it's right here. And then -3, -1, that's right here. And then 0, 0 is right here. Okay, so what we're getting is a parabola here. And that should have kind of been self-evident, right? We're dealing with a bunch of squares. Pun not intended, right? We're dealing with a bunch of squares. So then it's going to round out like this. And it's going to come up like this. It's going to go through this point. And it's going to keep going out like this, basically. So what we have is a slanted parabola right there. Right? A slanted parabola. Okay. Next, a three-dimensional vector function. Cosine t times I hat, sine t times j hat, and t times k hat. And remember, this is just the other way of saying the same thing with the pointy brackets, right? I could have done cosine t, comma sine t, comma t in the pointy brackets, and it would have been the same thing. I just wanted to display this the other way so that you can see it both ways. It doesn't matter which way you do it. It's just preferential to whatever application you're using at the time. Okay, now with this one, since it's got the trig functions in there, we need to use sort of a more common sense approach here. Okay, what I mean by common sense is we need to kind of see what's going on rather than just blindly plugging in points, because we could sit here forever getting a bunch of decimals that are hard to graph, or we can use a little bit of our curve knowledge that we've already seen to make sense out of this thing, right? So leave off the z direction for a moment and look, I've got x equals cosine t and y equals sine t. You should recognize that. That's a circle of radius 1, right? The radius is the number in front of the sine and cosine. A circle of radius 1. So in other words, if I were just looking at the xy, right, if it were just the y and the x axis, all I'd be seeing is a circle going around and around and around as t increases. You would just see, well actually you would see it like this, sorry, like this, right? It would just keep going round and round. Now, once you actually let the z-axis come out, then what's going to happen is I'm bringing in this third dimension, and look, it's just t. So as t gets bigger, z gets bigger. As t gets smaller, z gets smaller. It's just t. Okay? So I've got normally just the circle that does this, right? But if you bring out that third dimension, it's still going to be going around the circle like that. Okay? It's still going to be going around, but as t increases, z increases. So you've got this spiral going around like that. Okay? So from 2D, right, sine and cosine, you see this. But when you bring out that third dimension, you see something coming up while it goes around, right? Like a helix, a spiral. So let's see if we can get a quick approximation of that. Here's my z-axis. Here's my x-axis. And here's my y-axis. Right? Okay. Let's say this is x equals 1. Let's say that same distance here can be y equals 1. And what I want you to think about is the circle of radius 1. So in other words, if I can sort of get you to see this circle here of radius 1, that's in the xy plane. Okay? So sort of just in the plane there with that thing. It's going around inside of the xy plane there. Then the graph is going to be inside of the cylinder housed around that circle, right? If you look from above, all you're going to see is the circle. If you look from below, all you're going to see is the circle. So imagine this cylinder here. Basically, this curve is just going to be like wrapped on the surface of that cylinder, going around and around. Okay? And normally, remember, we start on the positive x-axis, so this is kind of like your t equals 0 point right here. So it's actually z equals 0 there also, right? So it's actually on the surface of the xy plane here. And then it rotates in a right-handed fashion. Remember, this is a right-handed system, and that's how we rotate our angles normally. That's exactly what's happening. But z is going to increase. So what we get is this cool spiral that's doing like this. And I'm really not doing this thing justice at all. Going around like this. Okay, and then the flow of your curve is this way. And that's not all it can do. It can also go underneath. Right? It'll go, if t is negative, it'll go down in underneath the plane as well. Okay? So sometimes graphing these curves has to be based off of just a little bit of what we've experienced before, especially if you want to get the 3D versions of these things. And then lastly, we've got all of our other function stuff going on, but we can also do the vector stuff. It's like we're merging these two powerful universes, and it gives us that much more information that I can try and analyze with these functions. That many more things that give me more variety in my universe of capability. Okay, so then the two functions here. The dot product works exactly as you would expect. I'll be doing the x component times the x component, the y component times the y component, the z component times the z component. So I've got 3t times 4 minus t plus 1 minus 9t times t plus t squared times negative 2. So then this becomes 12t minus 3t squared plus t minus 9t squared minus, whoops, yuck, sorry about that. I'm really apologizing to myself because I don't want to put the oils on the board. Minus 2t squared, like that. Okay, let me draw this separator here. Let's finish this up. Let's see, I've got negative 2t squared, negative 9t squared, and negative 3t squared for a total of negative 14t squared. And then I've got 12t plus t here, which gives me plus 13t. So that's what the dot product of the g function and the h function are. Now, one thing that you might be interested in when you're doing these things is you would be interested to know where this is equal to 0. Remember, that has an actual physical meaning. When a dot product is equal to 0, then two vectors are perpendicular, orthogonal to each other. So if I were to solve this to figure out what t values cause equal to 0, then I would be finding locations where these two vector functions are orthogonal to each other. And that can be important on so many other levels depending on how I want to relate g and h, right? This is not too difficult to solve. I can see that the dot product would be equal to 0, right? The dot equals 0 when t is 0, right? Or if I factor out a t and solve, it'll be when t is 13 over 14. So I actually have a couple of t values that if I were to plug them in, I would find sets of orthogonal vectors. And that might have a very important consequence for these two functions whenever they're engaged in a problem together. Knowing that they're at a right angle to each other for that particular point might be important. Cross product works exactly the same way as you've seen. To do the cross product of these two, I'm simply going to set them up in that determinant with I, j, and k. G function is 3t, 1 minus 9t, and t squared. The h function is 4 minus t, and negative 2. And remember, the way I always do my cross products are I take the other two columns and rewrite them, right? I have I and j. I'll have 3t, 1 minus 9t, 4 minus t, and t. Okay, so let's see what we get here. I have, for my I, I've got negative 2 times 1 minus 9t. So that's negative 2 plus 18t. And I'm going to leave, well, I'll keep some space here for that one beneath, right? I'll have another I coming from the other direction right here, from this one. that's going to be I times negative t cubed. Right? It's negative because that's a negative direction, a negative multiply line. This is a positive multiply line. Okay, plus j. I've got my two j's, right? The first one's going to be this one's a positive line. I have t squared times 4 minus t. So that's 4t squared minus t cubed. And then the negative j line is right here. Negative negative 2 is 2 times 3t is 6t. Right? And I'm going to be adding these things. Plus the k vector. I'll have my couple of k's here to finish that out. I've got my positive k line here, which gives me 3t squared. And then the other k line, which is my negative k line, is right here. And that one's the fun one. 4 minus t times 1 minus 9t. So that's going to give me 4. And then I'll have negative 36 and negative 1. So minus 37t. And then plus 9t squared. After I multiply those out, right? Okay, so then the resulting vector function, and remember, this is what we're doing. We're crossing two vector functions, and I'm getting a vector function back. I'm getting a vector function because it's going to have t's in it. For my first component, I've got these two added together. Negative t cubed plus 18t minus 2, comma. Here I've got these two added together, so that's negative t cubed plus 4t squared plus 6t, right? That's these two. And then I'll have these two. So 3t squared, 9t squared, that's 12t squared minus 37t plus 4, like so. And that would be my cross product vector function, right? And remember the function, the purpose of the cross product is to find that third vector that's perpendicular to both of the other two. And that's exactly what this vector function would generate, right? It would generate the set of vectors that's orthogonal to either one of these at a given t value, right? Being able to do the dot and cross product later on when we're evaluating all sorts of other operations on curves, including derivatives, is going to be crucial. Being able to do those sorts of things is going to give us another way of analyzing the way curves bend and twist and how we measure curvature and torsion while we have motion through space. Okay, so now let's go take a look at what some of these look like in GeoGebra, and then let's move on to some calculus examples.
I want to look at the two graphs that we had there. One was the 2D vector function, t squared minus 4 and t squared minus 2t. So as you can see for this one right here, if I were to have the negative t values, I'll just go up to negative 5 here, although you can't really see it on there. Anyway, you can see this side of the function is where it's progressing on the negative t values. And then of course as t progresses in the positive side, it draws the bottom part and then on out to the bottom infinite side there. And then some interesting points of course would be the point where t equals 0, which happens to be a vertical tangent, and then the next one when t equals 1, right here. The tangent happens to be horizontal there, or close to it. And then of course the point where it goes through the origin right here. where we have a normal looking tangent line there. Okay, so here's the graph of that one. The next graph that we looked at was the 3D vector function, cosine t, sine t, and t. In which case you were asked to look at this one to begin with like a two-dimensional. So that would be kind of like if I were looking at it like this. And then if I were to let the thing go, notice that what we get is the unit circle, right? The circle centered at 0, 0 with a radius of 1. However, the actual 3D version is much more interesting because it is going to spiral around a radius of 1 there, but as t increases, so does z. So we end up with a spiral curve like so. And you'll notice my z-axis is actually scaled by 5s as well. And that's the positive t values. The negative t values will spiral it below the axis. So I think you get the idea there. It's definitely a radius 1 circle spiraling around the z-axis there.
So you've already seen the basic structure for doing derivatives and integrals with vector functions that I showed you in scene 1. Here I just want to talk about some more of the consequences of analyzing derivatives of a vectorial nature, and talk about some of the ideas that can be focused upon when doing so, especially with derivatives. When it comes to vectors, the derivative vectors are extremely useful when looking at these curves and describing them in a more reality-based manner, realistic manner. Okay, so we have if you take a derivative with respect to t of some vector function, right? And remember, the difference between the vector function and a normal function is going to be that little arrow on top of it. So this is some vector function, and when I take the derivative, I get the prime of it, right? Which means I took the derivative of each component with respect to t, and we're going to call that the velocity vector function. Okay, sometimes they have v of t for that. I wasn't renaming anything in this particular scene, so we'll just keep it with r prime vector function. And then, of course, again, if you take the derivative with respect to t of the r prime vector function, you get the r double prime, the second derivative vector function of r, which we would call the acceleration. Not much of a surprise there, right? You did that in the one-dimensional normal function analysis. But here, they start to have a lot more meaning when we start dealing with them in a vectored quantity. Okay? So, for example, let's talk about these two derivatives of this thing that we just graphed a moment ago, right? So if I take the derivative of the vector function, right, f prime vector function, that derivative is going to be 2t, comma, 2t minus 2, like so. And then again, if I take the second derivative of that function, I'm going to go ahead and separate this out. The second derivative vector function, get the acceleration vector. Notice what I'm getting is just 2 and 2 for my vector function. So my second derivative vector function is a constant. Okay? That doesn't mean that it's not a function of t. What it means is the output is the same everywhere. And you've seen functions like this since algebra, like if I say f of x equals 10, right? We've seen constant functions before. That's what this is. This is a constant vector function now. At every point of t, this particular vector function issues the same vector. Okay, so let's look at a few values of both of these here. If I were to pick the value t equals to 0, right? Well, notice that f prime of 0 is 0, -2, vector, right? And t equals 0 is this point right here, by the way. Because if I do, remember, we already had this written down. At 0, we had -4 and 0, right? So that's this point right here. Now notice the f prime vector function is 0, -2. So if I issue that vector from this point, 0, -2 is this way. Just like that. All right. Well, let's check a few other ones, right? Let's do like f prime of 1. And that's going to give me 2, 0. And then let's also do f prime of 2. That's going to give me 4 and 2. Okay? Now, f of 1, as we saw in the last scene, was the -3, -1. Okay? So that's this point right here. And the vector right here, the velocity vector, is 2, 0. Okay? So that's this way, like this. Okay? But it's actually tangent. Okay? Remember, don't forget when you're doing these derivatives, we're calling it the velocity vector, the velocity vector function. Okay? But also don't forget that this particular vector function is going to be the tangent vector at any point. And notice that's exactly what I'm getting at each of these points here. F prime at 2, right? When I plug in 2, I'm getting the 0, 0 vector, which is going to be here, right? So 4, 2. 4, 2. I'm getting a tangent vector that looks like this. Okay? So notice this is exactly what's happening. I'm getting this sort of motion in the velocity vectors like that. And it's exactly what you expected. Whenever we were progressing the t value, right, the vectors are moving along the curve in this direction. So that's exactly what you would expect the tangent vectors to do. That's exactly what you would expect a velocity to be telling you. My velocity is moving in this direction at this moment. And then as it turns, well, how do we know it turns? Well, that's where the acceleration is going to come in. Acceleration is going to be present, and what's going to happen is it's going to be, accelerating, turning, twisting, whatever it happens to be doing. Notice what I can say is that it's the same at every point. The vector 2, 2 looks like this from the origin. That's the vector 2, 2 right there. Now imagine applying that same vector. Okay, 1, 2, 1, 2. Imagine applying that same vector at every point. Be right here. Let's see, 1, 2, 1, 2. Will be right here. Okay, so imagine that vector is applied everywhere. You see what's happening? My velocity, if I were to take a t value way over here, my velocity vector would actually be pointing in this direction. The tangent vector is going to be this way. Okay? But my acceleration vector is always at every point pointing this way. Okay? So the motion of the curve is such that it's coming this way, but it's constantly has this acceleration pulling against it. A force causes an acceleration, right? So it's constantly pulling this way. There's accelerations at every point. So it's like I'm going this way, and then I'm going to start slowing down and turning because it's pulling, and then all of a sudden it starts going this way. And it's also no coincidence to notice that if I were to find the focus, the vertex, and the directrix of this parabola, right? The vertex is going to be somewhere right here in the center. The directrix is going to be like this. And the focus is going to be right here. Okay? Notice that the vector 2, 2 is exactly perpendicular to that directrix. Okay? And it's exactly the tilt of the parabola. Not a coincidence. Right? That's the way parabolas are working here. So I've got this acceleration vector always pulling at all of those locations. But my velocity vector is always tangent, right? As if you graph the vector on those points, it's going to always be tangent to the curve like that. And then also the size of it tells you something. Actually, this one should be a lot bigger. I should have drawn that particular one bigger because it's not shrinking there. This one should be a lot bigger. Okay, notice these are smaller, and I actually graphed these to actual size using the coordinates here. And then I did the same thing with this one. It got a lot bigger as it goes out. It's starting to work with the pull, you see. It starts big here, and then it shrinks in size to here, and then it grows back out again as it's working with the vectors there. Okay, so there's a lot of purpose behind not just looking at these as vector functions. The derivatives are easier to talk about, and they have physical meaning, okay, and not just one way. They have direction, they have magnitude, all of that important information wrapped up into these little packages here. Okay, so flip around. We're still talking about derivatives. Don't forget, we still have the vector operations of addition, subtraction, scalar multiplication, dot product, and cross product. All of these things are vector operations that can be done to vector functions also. Now, addition and subtraction, not as interesting with derivatives because you just take the derivative of each one separately like any addition and subtraction. One thing we need to note is that there are 3 different types of multiplications involving vectors: scalar, dot, and cross. Scalar involves multiplying something that's not a vector with something that is. And all that is a distributive property. I would just be taking whatever this b of t is and distributing it to each of the quantities in each of the components of the a vector. Okay? But if you take the derivative of this, it actually obeys the old product rule that you've seen before. It obeys the rule that I could be multiplying normal b times the derivative of the vector function a plus the derivative of b times the vector function a. Same thing with dot product. If I'm dotting 2 vector functions and then taking a derivative, that's the same thing as if I were to do the derivatives independently and dotting them independently. So that would be a dot r prime plus a prime dot r. And of course I would still be getting a scalar result here, just some function of t. And then cross product, also exactly the same. But remember, with cross product, the order in which you're crossing the vectors matters. Okay, so you don't want to reverse any of the crosses when you're doing these derivatives here. Okay, so a cross r, then derivative, is the same thing as doing a crossed with r prime plus a prime crossed with r. Okay, so keep that in mind, that the loveliness of this, right? We're creating these vector function ideas, and yet built inside of it is the same stuff. That there tells you that you have stayed within the same structure of your calculus, and we've just made it more broad. We've just made the same system more versatile. Those rules still carry on up to the next level of the structure. Okay, this is the beauty of the structure of the vector and vector calculus here. Okay, so here's an example. This is the dot product of those 2 vector functions, and I want to show you how the derivative can be done both ways, right? So the derivative of the dot product of g and h, g dot h, would just be the derivative of this, which would give me negative 28 t plus 13, right? Okay. Now, if I take the derivative of each individual function and then do the dot product using the product rule, g prime of t is going to be 3, -9, and 2t. And then h prime vector function is going to be -1, 1, 0. It's a constant derivative on that one. Okay. So then g dot h prime plus g prime dot h vector functions. So g dot h prime, right? This is g, and I'm dotting it with h prime. So that's 3t times -1, 1 minus 9t times 1, t squared times 0. Okay, so 3t times -1 plus 1 times 1 minus 9t plus t squared times 0 is just 0. Plus g prime dot h. So g prime and then h, that's 3 times 4 minus t. And then -9 times t. And then 2t times -2. I'll just go ahead and multiply that out. -4t. Let's simplify here. I've got -3t. I've got plus 1 minus 9t. I have plus 12 minus 3t. I've got minus 9t minus 4t. Okie dokie. I have a 1 plus 12. There's your 13. Right? I have -3 minus 9 is -12 minus 15 minus 24 minus 28 t. Okay? Not a coincidence that it's the same as that, because vector functions follow the product rule structure for any kind of product. Scalar, dot, or cross product. They are completely different kinds of multiplications, all involving vectors in some sort of meaningful way, and yet all of them obey the product rule of derivatives. This truly is a marvelous insight into that structure of vector calculus instead of just normal calculus. Vector calculus is really what we're building here, so that you can talk more about the variety of this in multivariable calculus and how it applies to the much larger system ideas in multivariable calculus. Okay?
So here's that same graph that we were looking at in the last scene, but in this scene we were talking about the vectored quantities. So you can see right here I've got my position vector r, and at the different points that I can let my t-value be, you can see the r is basically just the vector pointing to all of those points. So it's just a position vector with respect to the origin. And at any one of those given points, if I take the derivative, I get the velocity vector, or the tangent vector, which of course you can see as this thing spins around, how the velocity vector decreases in size, and then as it's turning it stays kind of small, and then notice it starts to get large again. The green arrow is getting larger there as it increases along that end. Okay, so as we said before, the reason for this is because the second derivative, the acceleration, is constant. at every single point, it's the vector 2, 2. You'll notice right here, this vector is going to be constant the entire time. Notice that vector is not changing direction or size. The blue vector is constantly pulling in that one direction. And the velocity is the one that's changing size and turning. Right? Now, even though we didn't talk about it on the board, the same idea happens in three-dimensional space. If I take that same graph that we looked at, the spiral, right here, right? We have our position vector, which I have labeled as R there. And as we let this go around, you can see the R vector points to any position of the point that is on the curve there. Okay, so then to be most interesting, let's look at the derivative, the tangent vector. Notice it's in the orange right there. You can see that it's completely tangent at all times. The derivative vector is tangent there. Okay, but now in 3D you get the idea. The vector is not always in the plane. You see the vector is actually pointing upwards just a little bit right there. And as the point goes around, the velocity vector gives you the idea that it doesn't just go around, but it does actually have an upward velocity component. And of course, it would also have a second derivative, which you'll see right here. The interesting thing about this particular curve is that the second derivative vector always points to the center line. That's the kind of acceleration vector that causes circular motion. It has a constant inward pull that's always pointing towards the center. Kind of like grabbing a string and spinning it around the center of your fingers or something.
Now let's have some fun creating a very specific type of example that comes up a lot. In fact, we've already done an example like this several lectures ago where I used a certain quarterback's throw involving the time and the distance that it was thrown, and we were using parametric equations at the time. And it still applies here, but now that we have vector functions as an upgrade to parametric equations, you can see how much simpler the math flows for this topic. And also it raises some good, interesting points of how to do certain things with the vector quantities that we're going to be dealing with here. Okay, so projectile motion under a constant vector field. There's a few assumptions here that make this near the reality that you're accustomed to, but not exactly equal to the reality. And there are such subtle differences that you may not notice them yourself right away without some proper measurements. Okay, first of all, we are not using any sort of wind resistance for these projectiles, which in reality, the projectile would be slowed by certain amounts of wind resistance at different speeds. Also, technically, the gravitational field that we experience on a day-to-day basis is not a constant one. The strength of the actual gravitational field of a planet has to do with how far away you are from its center, the center of the planet. However, close to the surface of the Earth and within several tens of feet away, the force is barely noticeably different. So we're making the assumption that the gravitational field around us is constant for this type of problem. That's a huge assumption if you're doing a large scale of things, but we're not. We're keeping things within the surface of the Earth here. Projectile motion could be something that is fired from a cannon, maybe, or can be a ball that's thrown from a hand. It can be a car that jumps off of a ramp. Anything that when you hit time equals 0, in other words, ready, set, go, the object is only, it already has some sort of velocity, okay? And it's only under one other force after you hit go. And that force would be, in this case, the gravitational field pulling it downward. So it really doesn't matter if you do this in 3D or in 2D. The path of something that has only one constant field of force acting on it is going to be two-dimensional, even if you're in a 3D space. It's not going to waver side to side in any kind of way. It's just going to follow that path that it originally had, and then of course the constant field will act on it in that one pull dimension. So for example here, whatever projectile is started at some height, and it has some sort of initial velocity, some sort of initial speed in a certain direction. Okay, so there's a couple of things that you need to know there. The initial velocity, I would need to know the initial speed in which something is traveling, which is just the magnitude of the velocity. And by the way, you could do that with any tangent vector, like the ones we saw in the last scene. Any one of those, you could take the magnitude of the tangent vector, the velocity vector. If you take the magnitude of it, you would actually get the speed of which the particle or the object or whatever is traveling at that moment. Just the speed, okay? So that's just a magnitude question, okay? Speed is the magnitude of the velocity vector. And then, of course, in this case, the easy way for us to discuss direction would be an angle off of the horizontal that's parallel with the x-axis, okay? So if we know that angle and this initial speed, the magnitude, then we have the initial velocity at which the object is traveling at the very beginning. Now, of course, that's going to change. The velocity, initial velocity is pointing this way, but as you can see, as time goes on, the velocity vector would actually change direction at each one of these points, okay? So, we're making a few small assumptions there, right? And then we just need to know a few pieces of information, like the beginning height, the angle at which the initial speed is directed, the amount of initial speed, and yeah, that's the initial stuff that we need to know. And then of course we need to know the type of gravitational pull. We would need to know if we're in American or metric, right? In feet per second for the normal American units, and then for metric, meters per second is the customary. Feet per second is second squared, and meters per second second squared for those accelerations. And I threw the negatives in right here because naturally we tend to think of down as negative. You actually don't have to have that, but it's handy to put the negatives there, since everything else you're going to want to put positives, and the gravitational tends to pull the opposite, of the motion. So it's built into the A. The A has the built-in negative. The first thing you need to realize is, since that is the acceleration, right? The acceleration is why this thing is bent the way that it is, and it's a constant acceleration because we're in a constant vector field. That's the assumption, right? So that's my second derivative. My second derivative vector function would therefore be 0, a. It would be a constant vector function, because the acceleration is supposed to be the same everywhere. It's a constant vector field. Okay? So that would be my second derivative, because that's my acceleration. That's how the field is pulling the object. So that's an acceleration, since it's related to a force. Naturally, if that's an acceleration, now we can invoke some of the calculus that we discussed in the first scene, where I can integrate, right? I'm going to say now that my r prime of t is going to be the antiderivative dt of the second derivative vector function. In which case what I would be doing then is just doing the antiderivative of 0 dt and the antiderivative of a times dt, like so. And then naturally, of course, we're going to want to add in the initial velocity here, right? So then my velocity vector, my r prime of t, right? We can call that the velocity vector at t. Since we're not calling v anything else here, I'll call this the velocity vector, is the first derivative vector here. And I'm going to be doing this antiderivative here. The antiderivative of 0 is some number, right? I'll call it Vox. V naught, V0 is the initial velocity, okay? And then I'm saying in the x direction. And then here, the antiderivative is going to be AT plus some other constant, Voy. Now, how do I know that those are the initial values? Well, let's think about this for a second. If I let t equal 0, right? If I do r prime of 0, that's just going to plug in here. A times 0 is 0, and I'm going to end up with v naught x and v naught y. So that's why I'm labeling those two constants right here. Technically, what I did with these two is that after I did my integration, those are my plus c, right? Technically, this is my plus c in the x direction, and this is my plus c in the y direction. Those are my constants of integration. However, I labeled them very specially because I knew that if I plugged in 0 for the velocity vector, that those two numbers are the only thing left behind. And at time 0, that's this initial vector here. So then what I really need is just some components of that original vector. Okay, well, I've already labeled the magnitude as this little v naught here. And I'm supposed to know an angle to which this particular velocity vector is started at, right? Is directed at the very beginning. Okay, so if I want to break this into components, that's pretty easy to do with an angle. Remember, if I have this piece and this piece, right? I can break it into two component vectors that are at a right angle to each other, here and here, by using sine and cosine. Okay, so then my original vector pieces here, v naught in the x direction, is just v naught, the actual speed, the magnitude of the whole thing, times cosine of theta. Because it's this component right here. That's the x initial velocity, this component right here. Okay, that's Vox. Now, Voy, v naught y, same idea, but it just is sine theta. Okay, so that's my initial velocity vector. That's v naught velocity vector is equal to the derivative at t equals 0. The derivative at time 0 is the initial velocity vector. That's what we said. It started out at that velocity. So all I did was broke it into components, and since I knew an angle, I broke it into the angled components. And you've seen that when we've talked about unit vectors too. I just do cosine theta time, comma sine theta, not times. And then I have the v naught as the magnitude outside of it. And all I did was just distribute the v naught in. Okay, so what's the consequence of this? That means that my r prime of t here, right? My actual velocity vector at t, which is r prime of t, is equal to v naught cosine theta, comma, a times t plus v naught sine theta. And don't forget, a is actually probably a negative number, right? The a right there is probably a negative number, considering the formation of what we have here. So now I have a velocity vector function throughout the whole space. I plug in a number for t, and at any moment I'll have the velocity vector, the tangent vector at all the points. That's what I have. So let's do it again. Let's do the antiderivative and we'll get the position function, right? The position function, r of t. That's the goal here, right? I want to be able to predict where it's going to be. That's going to be the antiderivative of the velocity vector function. So therefore, I will be doing the antiderivative of each component. Like so. Now notice in the x component, I don't actually have any t's. It's just a number, whatever v naught cosine theta is, that's just some number, dt. So when I do the antiderivative of that, whoops, forgot my arrow there. My r of t is going to be like this. I'll have v naught times t times cosine theta. And I could do v naught cosine theta times t, that's fine as well. Whichever way you want to do it. Basically, it's just times t. Okay? Now, don't forget, I still need plus a constant, right? I still need plus a constant. We'll talk about that in a second. Over here, I'm going to have 1/2 t squared, because I'm doing the antiderivative, plus v naught t sine theta, that's the antiderivative of a number dt. And then don't forget, I also need plus cy, right? Some sort of integration constant. Okay? Just like before with the velocity, these constants end up being our initial values. How do we know that? Well, take a look. If I plug in the original function of 0, right? Just r of 0. That's the initial position over here, right? That's the starting position. Well, that was just 0 and h, because it had not traveled any in the x direction yet. So it's 0, but it's h, however much height, initial height off of the ground. So that's my initial bit here. But if I plug in 0 for t, notice this is 0 plus the constant. So in other words, my constant here must be 0. This must be 0 in order for this to be 0 when t is 0. Next, for this to be h, if I plug in 0, this is 0. If I plug in 0, this is 0. And therefore, 0 plus something has to equal h. That means that this constant of integration must be h, the initial height. Okay, so let's write down our result here. The actual position function, the vector position function, is equal to v naught t cosine theta, comma, 1/2 of a t squared plus v naught t sine theta plus h. And if you rewind and go back to one of the other video that had the parametric equation example, you would have seen this, but in components. And it was mostly just given to you. I know I'm a little crooked here. Sorry, I wasn't looking straight. But you get the idea. This is the x component at any point. This is the y component at any point. But it's based off of some variable t. Okay? We know t in this case is going to be time, but it doesn't have to be. It's some vector function of some parametrically defined variable t. In general, this could be some sort of motion controlled by just some outside variable. For our applications, the outside variable being t. Okay? So this right here, the r of t, the r prime of t, right, and the r double prime of t. Mixing those three together, we can answer any one of the questions that they usually ask about projectile motion. Let's go see an example. So I'd like to finish up with a fantastical projectile motion problem. It's sort of a fantasy, but it's good to get the old math juices flowing and to give you the right idea about the things that we can calculate while using these particular things the way that they are. Okay, so I have a car jumping off of a ramp. Okay, so it'll have some initial velocity when it leaves that ramp. Okay, now I'm saying that the car is moving up a straight ramp, so the directional angle that the ramp is will be the same that the directional angle of the initial velocity is. Okay, it jumps off of this ramp at 95 miles an hour, and therefore we will use that as our initial speed. Okay, so a few things. First of all, we need to find a lot of these different quantities that we usually would have in that formula that we were talking about, like the angle at which the initial velocity is. I need to have the correct units also, because all of our gravity calculations in America are feet in seconds, not miles an hour, and also of course calculating the angle itself, because it wasn't actually given, right? Usually it's much easier to measure the ramp like the way I've measured it here, and then we would calculate it. So some of the things that we would be interested in is, how high is the car going to reach as it's jumping? What is this peak height? How high can I get this thing to jump, right? How long before it crashes down on the ground? How long are you going to stay airborne, right? How far away will it crash into the ground, right? And crash is the operative word here, because if you go up high enough, not many cars are going to be able to survive the, it's going to, crash down. How far away is that, right? We want to know how far that is. And then another important thing, what is the car's speed when it actually contacts the ground? Notice I didn't say velocity, right? It's important to note that the velocity is the components split up in vector form, right? The speed is going to be the total, hey, how fast am I going when I impact this ground, right? Which goes directly to, in your physics classes, how you're going to calculate your kinetic energy and such and so forth, right? That's a very important question to know. Okay, so let's go through and figure out all of these things using the vector functions that we were just discussing in the last scene. So let's start with getting all of our initial stuff ducks in a row, if you will, right? So I can figure out my theta pretty quickly. Obviously the ramp is built to be a right triangle, so I can just say that the tangent of theta is 15 over 22, right? Okay, so tangent theta is 15 over 22. Therefore, theta is going to be arc tangent 15 over 22, which we have 34.286, 34.29. I'll use 34.29 degrees. Okay. Next, our acceleration due to gravity is going to be in American units, right? Because we're in miles an hour here, miles, which means our A, acceleration at any given moment, is going to be the negative 32, right? So if I pick my acceleration vector is going to be the 0, negative 32, and that's going to be measured in feet per second, right? That's feet per second squared. and therefore my velocity here, my initial velocity, my initial speed measurement is in the wrong units. So we need to fix that. I've got V naught is equal to 95 miles per 1 hour. And I want to convert this into feet per second, right? Because the acceleration is in feet per second per second. All right, let me separate this out a little bit here. We've got our theta. Let's get our V naught here converted in. There are 5,280 feet in 1 mile. So therefore I can get rid of my mile unit. So now I'm in feet per hour. And then there are, in 1 hour, 3,600 seconds, right? Because it's 60 times 60. 60 seconds in a minute, 60 minutes in an hour. I just went straight from hours to seconds. Did all my conversions, converting up there. Okay, so that's going to be in feet per second. So let's multiply this out. I'm going to have 95 times 5,280, and then I'm going to divide by 3,600. So I've got 139 point continuous 3. And that's going to be in feet per second. Okay, so now I've got my initial speed and I've got my initial angle for my trajectory. Okay, so basically just all of these two put together give me my initial velocity vector. Okay, so I can now set those pieces up. I also know my original acceleration vector. Okay, so let's start with setting up the r vector function, right? And its derivative to get the velocity function. So my position function, based off of what we were just talking about, is going to be V naught times cosine theta times t. Okay, so V naught is this times cosine of theta right here, right? And then times t. So I'll write that right here. This is V naught t cosine theta. That's this first component. But I know what V naught and theta are, so let's do those. 139 point continuous 3, and then times cosine of I'm getting 115.121. So 115.121 times t. Okay, so that's V naught cosine theta times t. Right, let me double check that real quick. 139 point bunch of 3s times cosine 34.29. Yeah, that'll work. We'll just do 0.12. Okay, comma. I'm going to have negative 16 t squared. Because remember, it's a divided by 2. And my a right now is negative 32 feet per second per second. Okay, plus, this is a over 2 t squared plus v naught t sine theta plus h, right? That was our original y component of the r vector function. So v naught times sine theta $78.5. Let's see. Let's double check that. Sine 34.29. Yeah, 78.5. 78.5. 5 times t plus the original height, which after he leaves the ramp, that original height is 15 feet. So plus 15. Okay, so I've got my original function here, the r of t, right? Which means that my velocity function, being the derivative of this, would just be the 115.12, which that's equal to just v naught cosine theta, right? Minus 32t plus 78.5. So there's my velocity function. And we've already said the acceleration, right, would be the derivative of this. And that just gives you the 0, negative 32 as speculated. Okay, so now how do we use these to our advantage? How high will the car reach at its maximum? Well, remember, at its maximum, I have a maximum point of the curve, which gives me a horizontal tangent, right? If it's a horizontal tangent, then that means the actual y component is 0. Okay, it's gonna notice the velocity vector function here. The x component is constant, right? It doesn't change with time. And that's because we made the assumption of no wind resistance. Gravity is pulling downward in the y direction, not the x. So it actually has no effect on the x velocity. The x direction's velocity is constant because we neglected any kind of wind resistance or any other drag or friction of any kind. Okay? So that's not what we're talking about. We're talking about it's going to go up, then it's going to come down. It's all y direction. Okay? So right here, I'll find the time when this thing is at a maximum by setting this component equal to 0. Okay? Think about it another way. If I have a horizontal tangent vector, right? If this is the max point right here, if this is the max point, then it's when the tangent line is horizontal. So imagine a horizontal tangent vector. The vector pointing this way would have to be some number, comma, 0. That's the only way it's going to be horizontal. Some number, comma, 0. So if we're looking for the maximum point, okay, then this needs to be equal to 0. So that's our next point right here. The max location. Let's start by finding the time. 0 is equal to negative 32t plus 78.5. So naturally, the t amount here is going to be the 78.5 divided by 32. Okay. Divided by 32. And I have 2.453. Let's just say approximately 2.45 seconds. Okay, so that's how much time it's in the air as it reaches its maximum. And to be honest with you, if I was in that car, 2.5 seconds would be a long time. 1 Mississippi, 2 Mississippi and a half, right? That would be like feeling like a forever as you're soaring up. And that's just as it reaches the peak, right? So now, how high does the thing actually get? Well, to figure that out, okay, the actual max height is going to be the y component. So that's going to be r sub y of 2.45. Right? So whatever that value is, I'm just looking for the y component. How high is it off the ground? If I do the whole vector and get the x component, that's just going to be how far away is it, right, from this origination point. How far would this be from here to here? Okay, that would be the r sub x of the 2.45. Okay, so let's actually do that calculation. I'm going to take the 2.45 and I'm going to plug it into the t-values for this piece right here. Okay, so I've got that answer. The 2.45 is already programmed in my answer. So I'm just going to hit negative 16 times answer squared plus 78.5 times original answer plus 15. And I'm getting 111.3 basically. Feet. Remember how I said this problem is going to seem fantastical, right? You probably would not want to be in the car that jumps over 100 feet in the air. You better have some really good shock absorbers and some really soft mud at the other side of that thing, right? This car is destined for demolition after this jump. Could be a really heavy car. But in any case, so we found the maximum height, right? That's the answer to part A here. It reaches a maximum height of around 111-ish feet off the ground. Okay, so next, how long before it crashes down on the ground, right? So how long is it going to take to get from here to here? And to be honest with you, the next two questions are really the more important ones, right? I would have to answer B whether it was asked or not, because T is controlling this vector function, right? T is controlling this vector function. So really, to find out the answer to any of these things, to either one of those, right, I need to plug in a T value. So I need to answer B first, and then the other two kind of just follow along after I plug it in. Okay, so how long before it crashes down on the ground? Well, hitting the ground means that the height is 0, right? So in other words, for letter B here, that's going to happen when R sub y is going to be 0. The y component of the position function is going to be 0. The height, right? The y component here is going to be 0. It's hitting the ground. So therefore, that's what I'm going to solve first. Ry is equal to 0. Okay, so let's do that one. I have negative 16t squared plus 78.5t plus 15 is equal to 0. And then that's a quadratic equation. And I'm just going to solve it with the quadratic formula. Right, so t is equal to negative 78.5 plus or minus square root 78.5 squared 4 times negative 16 times 15 all over 2 times negative 16. Now don't forget, we talked about this the last time we did a problem like this, you're going to get two answers here because technically we're talking about a parabola and it actually has imaginary ground point on this side. If you were to take this parabola and progress it, negatively, it would be the level of the ground over here. But that piece of the parabola doesn't exist for us. Okay? That's before he left the ramp, and therefore there was no path before the ramp. It doesn't make sense. So one of these two answers is going to be nonsensical. Okay? The negative one, naturally. Notice there's a negative in the denominator here. So when this is negative, it always is, when this is negative, and then this is negative, I'm getting all three negatives, which is going to make the whole thing a big old positive. But when this is positive, I'm actually going to get, something really big positive here. Minus this is going to give me a positive still. Divided by a negative is going to give me a negative. So here's what's going to happen. I'm only going to be focusing on the minus direction here, because that's the one that I need. If you want to go ahead and plug in both of them, you'll see. The plus one is going to give me a negative answer after I do this whole calculation. The minus one is going to give me a positive value that's going to represent the time when it hits the ground further down the line. Okay? So I'm not worried about the plus here. I'm just going to be doing the minus. Okay? So let's actually do that. 78.5 squared. Double negative here, that's just plus 4 times 16 times 15. So 64 times 15. Okay, square root that. Naturally. Plus 78.5. And I'm going to divide by 32. So I get 5.09. seconds. Notice how that kind of makes sense, right? It hit that maximum height at around 2.5 seconds, right? The 2.45. It's actually not halfway, because if you think about it, he already had some of the distance already covered, by the ramp, and then he had to actually make up for that last 15 as he's coming back down. So technically this is a little before half, and the 5.09 is has a little bit more on the after part of it than it does before. But in any case, it's close to half, right? It makes sense. Most of the traveling is above the ramp's height, and then just that little bit of 15 feet afterward is not that much to cover. So anyway, 5.09 seconds later, crash into the ground. Okay, so that's the answer to part B. How far away will it hit the ground? Well, guess what? All that is the x component of the position vector, right? The x component is how far away from this t equals 0 point, which is when it leaves the ramp, right? So if I plug in the answer to C here, the answer to C is just going to be r sub x of 5.09. Okay? Well, notice that's just a multiplication, right? Because this was at a constant x velocity. I've got the 115.12 times 5.09. And I've got that it's really, really close to 586 feet. That's part C. Now, part D. What is the car's speed when it hits the ground? Okay? Now I have here a velocity vector function. I want to know the speed when it hits the ground. So, here's what we're going to do. For letter D, I'm going to find the velocity at the point at which it hits the ground. But remember, the velocity at 5.09 is a vector. It's the vector 115.12, right? Because the x component of v is constant. And then I'll be doing negative 32 times the 5.09 plus the 78.5. Okay? So negative 32 times 5.09 plus 78.5. I'm getting negative 84.38. So this is the velocity vector as it's coming down. So this is the way the vector is pointing, right, is in the direction of this vector. But that's not the speed. Remember, the speed is the magnitude of your velocity vector. It is the magnitude of your tangent vector, your derivative vector. Magnitude is your actual speed here. Okay, so my speed is equal to the square root of 115.12 squared plus 84.38 squared. Yes, I know this was negative, but it's squared, so it doesn't matter, right? That's the only reason I'm doing that. So the speed at which I will strike the ground will be approximately equal to square root of 115.12 squared plus 4.38 squared, 142.7, and that's in feet per second, right? Now, of course, in everyday conversation, I imagine we would probably like to see that in miles per hour, because that's what we're accustomed to thinking of speeds in, right? So let's do the opposite conversion of the feet per second that we did up here, right? And convert this back into miles an hour for ourselves. Just for just for fun, 142.7 feet per 1 second. So that would be times 360 seconds to give me 1 hour, and then times or divided by 5,280 feet to give me 1 mile, right? So it'll be approximately what? Times 3,600 divide by 5,280, approximately 97.3 miles per hour. Either one of those, it didn't specify which units to give the answer in, so either one of those would have been acceptable as far as the speed is concerned. Still a striking speed, right? Pun intended. Something that would be quite disastrous. Hitting the ground would be that particular speed. So I hope this problem and I hope this whole lecture has helped you understand how vector functions is a really convenient and awesome upgrade to parametric equations, and it can actually be carried even further than this. I hope that you don't stop with your calculus studies here. After this, to continue on into multivariable calculus. I do include one more lecture on partial derivatives for Calc 2, but other than that, this is really where we finish Calc 2. I urge you to push yourself to try multivariable calculus and expand your experiences on these sorts of functions.